In this video, I'm going to talk about the paper by Marco Battaglini, Econometrica 2002. So the link to the paper is on the website. This paper deals with multidimensional cheap talk with multiple speakers. So far we have looked at the Crawford-Sobel model, the very simple and stark version, where there's only one dimension of uncertainty. There's one random variable which the decision maker does not know, and there's a single expert who can potentially convey that information about that unknown to the decision maker, the receiver. And what was the broad lesson we learned? The broad lesson was that if the decision maker is, if the expert or the speaker is biased relative to the different decision maker, has different preferences, then the exact information is impossible to convey because of credibility problems. So the information gets coarsened, it gets divided into a number of intervals, and within the interval, fine information cannot be conveyed. And secondly, the bias of the sender is important. If the sender is extremely biased relative to the decision maker, then the only equilibrium possible is the babbling equilibrium, in which no meaningful information gets across. So what Battaglini says in this paper is that in more complex problems, where there's more than one dimension of uncertainty, and there may be sort of multiple speakers, multiple experts, multiple advisors to the decision maker, it's possible to extract more information. Okay. So what are examples of multiple dimensions? So for example, the government has to allocate funds between multiple ends. There's an allocation to defense, there's an allocation to the social sector, poverty removal, and allocation to other needs, right? So how much money to allocate to guns, how much to butter? That's one kind of multidimensional problem. Investing in infrastructure versus poverty. When the university is allocating funds, some funds are allocated to teaching, some to research. So how much money should go into each of the budget segments? So Battaglini's main point here is that, first of all, with two or more dimensions, fine information can be transmitted along one dimension. So if you have a two-dimensional problem, along one dimension, fine information can be conveyed. I'll make that clear as we go along. More importantly, if you have multiple dimensions and multiple experts, the informational possibilities really go up significantly. In fact, the receiver or the decision maker can learn full information about the state of the world by playing off the biases of the experts against each other. So it doesn't matter that these experts have different preferences from the decision maker, as long as they have different preferences also from each other. Then by using their biases against each other, the decision maker can learn a lot of information. In fact, it's possible for the decision maker to learn everything. So informational possibilities really go up. And in fact, unlike in the single dimension case, with multiple dimensions, the size of the bias, how different an action these various experts would like to choose relative to the decision maker, the size of the bias becomes unimportant. Even with very large biases, as long as the biases are different from each other, the decision maker or the receiver can learn everything. So that's a very strong and interesting result that we will see. If the expert's information is slightly noisy, so that if the experts don't perfectly know the state of the world, they know it only with a little bit of noise, this property that we just discussed goes through, right? So it's robust to experts having slightly noisy information. So to bring out the main message of the paper, I will start with the case of two dimensions, but a single expert. Let me amplify the message a little bit more before I start on the mathematical model. One illustration of the point that we're trying to make here is there in a book by the historian Doris Goodwin, who has a biography of Lincoln, which is titled Cabinet of Rivals. So Lincoln created a cabinet which was very diverse. It included people, a lot of whom had a lot of disagreements with Lincoln and with each other. So his cabinet was not homogeneous. It was not consisting of very like-minded people. It was a very motley crew, a very diverse set of people. And according to the historian Doris Goodwin, that was a good thing, because Lincoln got rich advice from this wide array of experts, and that allowed him to make. Okay, so I'll start with a simpler version of the problem. I'll start with the problem with two dimensions, or two unknowns, and a single expert. And we'll get some intuition from that model. And then I'll bring in a second expert and we'll see what happens. Okay, so there's a state of the world which is now a vector. So there are two random variables, θ1, θ2, and we'll take the uniform distribution as we have been doing previously. Each of them are independently drawn from a uniform distribution on 0, 1. Example, let's say θ1 is the level of external threat that will determine how much the defense budget should be, and suppose θ2 is the extent of poverty, which should determine the how much money should be allocated to world welfare programs. The action choices are going to be a vector, two-dimensional vector, A1, A2. So A1 is like the defense budget and A2 is the social sector budget. And here are the preferences of the receiver and the sender. It's like before. I've omitted the negative sign. So think of these as being disutilities, which each side is trying to minimize. And it's the previous quadratic form, except that we have two-dimensional information and two-dimensional actions. So we'll just add up the square of the errors, right? And for the sender, we'll use the bias B on each dimension. So the sender now has a bias vector, B and B. So that essentially means that if both of them knew the state of the world, the sender would ideally want to allocate B amount of more funds to each of the budgets, the defense budget and the social sector budget. So so that's the bias vector now, and it has a slope of 1, and the orthogonal vector to that bias vector has a slope of -1, right? What that means is, let me draw a picture to make it clear what I mean. So this is our state space. State of the world consists of some θ1 and some θ2. and we'll also measure the actions along these two axes. And so suppose the state of the world actually is here. So these are the values of theta 1 and theta 2. So if the receiver knew the state of the world, the receiver would choose this action. So this is the receiver's bliss point. The way I have set up the model, the sender's bliss point or ideal action is higher by b on each axis, right? So if you join a line between these two, this has a slope of 1. And now if I draw another line which is 90 degree to this bias vector, so that will be in this direction. This is 90 degrees. And this has a slope of -1. Okay, this orthogonal vector, the vector which is orthogonal to the direction of bias. And one of the observations that lead to the point that Battaglini is making in this paper, one of the observations is that there is full incentive to reveal partial information along this dimension, along the blue line. So along that dimension, there really is no bias. So I'll show you what that exactly means. It'll become clearer, but that's the sort of summary or takeaway. All right. So now that's our model, and we want to look at perfect Bayesian equilibrium of this cheap talk game with two unknowns. So as usual, we'll have a message strategy of the sender. There will be an action strategy of the receiver, action as a function of message. And each message is going to lead to some updated beliefs, which is captured in this conditional probability function. Now, one kind of equilibrium is where we have disconnected cheap talk, meaning that there's one message which purely conveys information about theta 1, another message which conveys information about theta 2, and these are not linked up, right? So we can, along each axis, we can create the familiar Crawford-Sobel partition equilibrium, that the possible values of theta 1 are broken up into a number of intervals. Similarly for theta 2, and that's how communication goes. If the value of b is large, then in this kind of disconnected cheap talk, the only possible equilibrium is babbling in each dimension, as we saw earlier. Yes. So in particular, if b is greater than 1/4, we have seen before that the only possibility is babbling. And then essentially the receiver will not receive any meaningful information. So on each dimension, the receiver will choose an action which is the expected value on that dimension, namely half. What I want to show you is that instead of this sort of disconnected cheap talk, there's another possibility, which is comprehensive cheap talk. So in that kind of equilibrium, in this last kind of equilibrium, the sender reports some sort of relationship between theta 1 and theta 2. And that leads to better information transmission possibilities. This is what I said earlier. So let me show you one particular kind of equilibrium of the latter sort. Right? So the sender strategy in this equilibrium is going to be a message which reports the difference between the two random variables, theta 1 minus theta 2. So the message captures the difference. And the receiver's beliefs reflect that. So the receiver, after hearing the message, will know what the difference between the random variables is. And so the receiver's belief will be a uniform distribution on this straight line. So if you look at this, right, for a given value of m, this is the equation of a straight line with slope +1. So from the message, the receiver will figure out what the difference is. So the receiver will be able to identify a line on which the θ1, θ2 vector lies. And his beliefs, given that it's uniform distribution on the square, his updated posterior beliefs will basically become on a line. And then the receiver's strategy will be to choose the midpoint of that line, which if you solve it, you will find that the coordinates are 1 plus m divided by 2 and 1 minus m divided by 2. And if you add them up, you will find that a plus the sum of the two actions always equals 1. Let me move to a picture to illustrate what I'm talking about here. So, if this is the sender's strategy, then θ1 minus θ2 equal to m. The moment some value of m is specified, the moment the message takes a particular value, that becomes an equation, a straight line like this. Okay? So for a given m, we know that this bold line, or the receiver knows that the state of the world, whatever it is, it lies on this bold line. And if you change the value of the message, if you change the value of n, it becomes another line in this class, right? All of these lines have a slope of 1. They only differ in the value of the intercept on the vertical axis, and that value of the intercept is determined by what the value of m here is. Okay? Now, a particular message has been sent, a particular value of m has been specified, a particular message has gone through. So that allows the receiver to conclude that the state of the world lies on this straight line. So what is as you know, in these uniform quadratic models, the optimal choice is always going to be the expected values of theta. So if the receiver learns that theta lies on this straight line, the expected value is the midpoint of the straight line. Okay? And for any of these other straight lines, which will arise for other values of the message, the expected state will be their midpoints, and so those will be the actions chosen. Okay? So, in other words, in the equilibrium that I am describing here, the sender essentially points to this family of straight lines, points to one among this family of straight lines, and essentially says that the state of the world lies on this straight line. And immediately the receiver goes ahead and chooses the midpoint of that straight line. That's what these red dots are. And we can connect these red dots. That gives us this red line, which is the locus of all possible actions in this equilibrium. So the sender, by varying his message, can change the action of the receiver along this red line. Right? The red line is the connection of all the midpoints of these blue lines, the family of blue lines that I was talking about. And you can easily calculate that the coordinate of these midpoints will be given by these values, 1 plus m by 2 and 1 minus m by 2. Okay. Now, how do we know that this is an equilibrium? Well, to be an equilibrium, the sender has to be playing a best response, the receiver has to be playing a best response, and the beliefs of the receiver have to be rational. They have to be Bayes compatible. Now, the way we have constructed this takes care of 2 out of 3. Okay? When the receiver is choosing the midpoint of these straight lines, that guarantees that he's playing a best response, right? He's setting his actions equal to the expected values of the state. And also the beliefs of the receiver are rational. They can be derived from Bayes' rule. Basically, the beliefs do follow from the strategy that the sender is using. So the only thing that we need to check is whether the sender's strategy is optimal or a best response. Okay. So to check that, we can do the following exercise. So this is what the sender is trying to minimize, right? The sum of the deviations from his desired actions. So this is what he's trying to minimize. We have specified the action choice rule, or we know the receiver's strategy, so we have inserted that in this function. And now the sender will choose the value of m, the value of the message, to minimize this. So that's a simple problem. You write down the first order condition. The derivative of this has to be equal to 0. So that gives you this equation. Okay. And when you solve this equation, you find that the optimal message is indeed theta 1 minus theta 2. Okay. So we have ticked the last box. The sender is paying a best response in this construction. So it's indeed an equilibrium. We can see the same result as a credible delegation. Okay, so you can sort of think of this as the receiver saying, I'll let you choose the action with some sort of a budget constraint. Yes, A1 plus A2 has to add up to 1. You cannot deviate from that. But given that budget line, you have to stay on that budget line, but you can choose any point on that budget line. And there again, you can check that the actions that the sender will choose will end up to be what we had in this equilibrium. If you go back to the picture, if the red line is the budget line which has been given, then he'll choose the sender will choose the appropriate action. Let me further show you the geometry of this. So suppose the true value of theta lies on this bold blue line. Okay, it lies somewhere there. And suppose the sender's bliss point is theta plus b, this dark point. Okay, so that's what the sender would ideally want. But the sender knows that she doesn't have the luxury to choose this point. Right? Her messages will only induce an action vector which lies on the red line. So the question boils down to, when this is the sender's bliss point, which point on the red line does she like best? Okay, and the answer to that is indeed this red point. Okay, it's the point which is the intersection of the budget line, if you will, and this bold blue line, right? Because the red line, the budget line, and this blue line, they are at 90 degrees to each other. And remember that the sender's disutility is the sum of squares, which is the equation of a circle, right? So at this point, there's a tangency between the sender's indifference curve and the budget line. Okay, so this point is closest. So even though the sender could point to some other one of these dotted lines, and that would induce an action which is any of these other red dots, they're further away from his bliss point. Okay, so he doesn't want to lie. He wants to genuinely, truthfully say that the state of the world lies on this blue line, on this bold blue line, instead of pointing to one of the other lines, because then he will end up getting an action which is further from his bliss point. And similarly for any other value of the state of the world. Okay, so imagine that, going back to the illustrative example that I was talking about. Let's say the Prime Minister has an advisor, and the advisor advises the Prime Minister on both the level of external threat and the level of poverty, and so therefore the defense budget and the social sector budget. And suppose there's an upward bias which the expert has. The expert wants to have a bigger budget for both the defense and the social sector. So the expert will have a tendency to exaggerate both the external threat and conditions of poverty on the ground. But if the Prime Minister says that, okay, I'll give you a total budget for defense and social sector spending, and I'll let you choose its allocation, right? So for a given budget, the incentive for the expert to choose a wrong allocation is not there. So once the total amount of money is fixed, the expert will put more money in defense if the external threat is relatively strong relative to poverty, and vice versa. And on the question of allocation of a given amount of money, the expert really doesn't have any bias relative to the Prime Minister or the decision maker. So that's why the allocation can be left to the expert, but not the overall size of the budget. On that, some limitation has to be placed. So that's a useful insight that, even though there are biases on each front, in terms of composition, in terms of sort of relative allocation, there's no bias. And more mathematically speaking, the expert in this illustrative example has a bias which is in a direction with slope -1. And what the expert can reliably do is reveal information in a direction along the red line, which is orthogonal to his direction of bias. And so that is the property, that is the feature which will be exploited in the construction that we are going to talk about. So now we are going to think about this two-dimensional problem, but there are two different experts, not just one, and their bias vectors are different. So now we are going to talk about the case of two dimensions and two experts. So it's the same model that we were talking about. We'll just bring in a second expert into the picture. And we'll consider the case of very general biases of these experts. So the first expert has biases B1 and B2 along the two dimensions. And the second expert has biases B1 prime and B2 prime. Okay. And will allow very general values of B1 and B2. Okay, and the game is, as before, the experts simultaneously send messages M and M prime. And the receiver, after hearing the two messages, draws some conclusions and chooses an action vector A1 and A2. So if we're talking about equilibrium, what are the strategies and beliefs? Well, the expert strategies are of this form. So each expert knows both theta 1, theta 2, right? They know both the unknown, the random variables, their realization. And each has a message strategy of this form. The message is some number which they convey to the receiver, and the number is a function of theta 1 as well as theta 2. The receiver formulates some belief about what possible theta might be based on the two messages. That's captured by this G function. And the receiver strategy is to choose an action on each dimension as a function of the two messages that have been heard. Okay, so that describes strategies and beliefs. And as usual, we want to look at a perfect Bayesian equilibrium, meaning both players are playing best responses and the receiver's beliefs are justified. They can be derived from the strategy of the two speakers. Now, to understand what's going on, it's useful to look at a special case, which is the case of orthogonal biases. So that's what I'll look at first, and then I will tell you the logic of the more general case. So in this special case, each expert is biased along only one of the two dimensions. So think of the two advisors to the Prime Minister, advising the Prime Minister about the, how much money to allocate to defense and to welfare programs. The first expert is a defense hawk. So the first expert wants to allocate more funds to the defense budget compared to the Prime Minister, but has no bias as far as the social sector budget is concerned, right? So suppose that's what the first expert is like. And the second expert is similar, except that the second expert wants to inflate the social sector budget, but has identical preferences as the Prime Minister with respect to the defense budget. Okay, so their biases are along only one of the two dimensions and along different dimensions. Okay, so that means that their bias vectors of the first expert is 0 and p. He has a bias on the defense budget, and the other expert has a bias b prime on the social sector budget. Okay, now if you step back and think about it intuitively, right, there's an easy solution to this problem as far as the PM is concerned. Just consult the expert on the issue on which he is not biased. Okay, so there's this defense hawk. Don't ask him how much money should be allocated to defense. The defense hawk has no bias on poverty alleviation and the social sector. So just ask him how much funds should be allocated to the social sector, and he'll tell you the truth. And similarly, the other expert is a bleeding heart who wants more money to go into the social sector budget than what the Prime Minister finds optimal. So don't ask him about the social sector budget. Ask him about the defense budget. And again, he'll tell you the truth. So consult the expert on the issue on which the expert has no bias. And don't bother to ask him about the other issue on which he has a bias. So that seems to be the intuitive solution to this situation. And indeed it is. So now we're going to check the maths and satisfy ourselves that this intuition is true. But the intuition is not very hard to see. So we can now construct an equilibrium where the first expert's message really reflects theta 1. Remember, the first expert has no bias on the first of the two random variables. So the first expert sends a message which is just the true value of theta 1. The second expert sends a message which is the true value of theta 2. And the Prime Minister matches the first action, right, the social sector budget, let's say, to the message of the first expert, and the defense budget to the message of the second expert. Yeah. So these are the strategies, and the beliefs are correspondingly. Now, why is this optimal? We have to check that whether the experts are doing the right thing, and that is very easy. Expert I can only influence this part, this is the component on which the expert is not biased. So the expert is really going to try and send a message which minimizes this, and the optimum is theta 1. Let me go to the picture, and that will perhaps make it clearer. Okay, so the first expert, let's say the true value of the state of the world is this black dot, right? This is what the true combination of theta 1, theta 2 is. Now the first expert is unbiased on the horizontal dimension, is only biased on the vertical dimension, wants a higher value as far as the second action is concerned. So if this is the true state of the world, this is what the decision maker would ideally want to choose in terms of the action vector. And the bliss point of the first expert is vertically up, this blue dot, right? So it's theta plus b on this dimension. Now, given this equilibrium construction, the decision maker, the receiver, does not listen to our expert about the value of theta 2. The decision maker's strategy is to choose theta 2 based on the message of the other guy, of the other expert, right? So this person cannot influence matters in the vertical direction at all. But he can fully influence the action choice A1. His message will not affect A2 whatsoever, but his message will affect A1. And so what are the possible choices that he faces? Well, let's say the other expert will tell the truth about theta 2. Right? The other expert is unbiased on this dimension, and the decision maker listens to that expert. So let's assume that the other expert will tell the truth. So that means the choice of A2 is given by this line. Okay. Now, the expert we are looking at can only affect action A1 by changing his message. So effectively, he can induce an action choice, an action vector, which is this horizontal line, right? He can only change the value of the first coordinate through his message, but not the value of the second coordinate. So the problem this expert faces is that when his bliss point is this blue dot, when this is what he would ideally like to choose, he can only influence the action along this blue line. So the question boils down to which point on this blue line is closest to his bliss point. And that is given by the true state of the world, right? Along the blue line, that's the point he wants to choose, because that's where his indifference curve is tangent to the line of influence, right? It's really the perpendicular. If you drop, so if he's choosing a point on this line, he would want to choose a point so that it's a perpendicular from his bliss point, right? And that's, as you can see from the picture, is the true value of the state of the world. And for the other expert, it is identical. The other expert, again, this is the true value of the state of the world. The other expert's bias is along the horizontal axis. So the other expert's bliss point is in this direction, right? So it's this pink dot. And the other expert can only influence matters along this vertical line. Yes, his message will shift the action along this vertical line. And so which point on the vertical line does he like best? Well, the true value of the state of the world. So he will truthfully report the value of theta 2. And so the decision maker can combine each expert we have just discussed would like to report the variable on which he is unbiased truthfully. So the decision maker can combine those two reports, and from that the decision maker figures out theta 1 and theta 2 exactly, and so that means all the relevant information becomes known. Now, this is of course a special case, but the special case gives us some intuition about what might happen in the more general case. In the more general case, they may have biases on each dimension, on each action choice. But as you can see in the special case, each expert is biased along one axis. Right? The bias vector is either horizontal or vertical. But what we see in these pictures is that, for example, this expert has a bias which is towards the right in a horizontal direction. But the expert has the incentive to tell the truth in the vertical direction, right? Along this pink line. And the other expert has a bias in the vertical direction, but has full incentive to tell the truth in the horizontal direction. Okay? So the more general idea there is that each expert has an incentive to tell the truth in a direction which is at 90 degrees to the direction of the expert's bias, orthogonal to the direction of the expert's bias. And that is what can be exploited to create an equilibrium where all information spills out and the receiver essentially knows the exact value of the state of the world. All that we need is the expert's biases are not in exactly the same direction, or their bias vectors are linearly independent. They don't have to be at 90 degrees to each other. They only have to be in different directions from each other. And then we can make them tell truth in along two different lines, and combining that, we can figure out what the exact state of the world is. So let me give you the maths of it. Yes, and again, I'll go back to pictures to explain it more intuitively. So here's the full construction. These are the message strategies of the experts. Okay, so I'll give you the strategies of the experts, and I will show you that each of them is playing a best response. So we'll check the maths, but I'll link it to the intuition. So the first expert's message strategy is to report the value of some linear combination of theta 1, theta 2. And notice that the coefficients are the biases of the other expert. Okay, and similarly over here. So each of them reports what is the value of some linear combination of the two unknowns, the two random variables. Okay, so suppose they're following this strategy and the receiver knows that. Okay, so the receiver, once the two messages have come through, right? Some value of this and some value of this has been heard. The receiver can solve this pair of simultaneous equations. Yes, solve for theta 1 and theta 2. And if you do the solution, you will find that these are the expressions you get. Okay, so if the receiver believes that these are the strategies, message strategies of the two experts, then by solving the two simultaneous equations, the receiver can figure out the values of theta 1, theta 2. They're given by these two things. And so those are the actions which the receiver will choose. Okay, so these numbers are just solutions to the pair of the simultaneous equations. Okay, and receiver's beliefs is indeed these are the values. Okay, so in this construction, the receiver's actions and the receiver's beliefs are derived rationally from the message strategies of the experts or the senders, and the receiver's strategy is also optimum by construction. Okay, so two pieces of the construction we don't have to check. The receiver is forming beliefs and choosing a strategy in an optimal manner. All we need to check is whether, given that this is the receiver strategy, whether these experts are indeed following an optimal message strategy, whether it's in their interest to truthfully report these linear combinations of theta 1 and theta 2. And we'll show that that is indeed the case. So let me skip ahead to the maths and I'll come back to this. So here's how to check that. Each expert will take the other expert's message strategy as given, as well as the receiver's reaction function as given. So let's focus on expert 1, the first expert. The first expert knows that these are the actions the receiver will choose, okay, as a function of the two messages, M and M prime. And we can do the substitution. On the previous slide, we had derived what these action choices are, so we have substituted that over here. Now, this expert, expert 1, has no control over M prime. Okay, but the expert believes that the other expert will choose M prime according to the strategy that was in the previous slide. Okay, so this expert's problem boils down to minimizing this sum of squared errors, or the sum of squared deviations from his own bliss point, and that's the expression that we have over here. So he's going to minimize this. Yes, he has already incorporated the receiver's equilibrium strategy, and he's also going to incorporate the other expert's equilibrium strategy as specified in the previous slide. And then he's going to choose his own M to minimize this expression. And what we are going to see is that his optimal M indeed follows this rule. His optimum M will end up being this value. So that's easy to check. You write down the first order condition. Okay. First derivative of this equal to 0. So when you do that, you get this. This is just equating the derivative to 0. That simplifies to this, right? This, remember, was the equilibrium action of the receiver. So I've sort of substituted that back. Now, in equilibrium, each of the action is supposed to, so what we have to check is whether at equilibrium this first order condition or this best response property is satisfied. So in equilibrium, each action choice is supposed to match the corresponding state. So A1 will end up being theta 1 and A2 will end up being theta 2. If that is true, then let's do the substitution. Let's replace A1 by theta 1, A2 by theta 2, and see whether this equation is satisfied. Right? If it is satisfied, then we are done. Then that means that each expert has an incentive to follow the message strategy that we wrote down. So if you do the substitution, you substitute theta 1 here and it cancels out with this theta 1. So on the left hand side we have minus b1 times b2, and over here this theta 2 will cancel out with this theta 2, and so on the right hand side we end up with the same expression, which is minus b1 times b2. Okay, so indeed the left hand and the right hand sides are equal. Yes. So that means that each of these experts, given the equilibrium strategy of the receiver and the other expert, each expert is indeed playing a best response when the expert is following the message strategies that I wrote down over here. To check the optimality of the other expert, it's essentially the same exercise, and we can check whether the first order condition is being satisfied. So that's showing it mathematically. Let me return to the diagram to explain it a little bit more. So this is the general case. So suppose, by the way, all these question marks, as I've, in all these pictures, the question marks essentially are thetas. So read all the question marks as theta. So let's say this black dot over here is the true state of the world. So we are looking at one of the two experts, and that expert has a bias in some arbitrary direction. So let's say when the true state of the world is this, and so the receiver's ideal action is this. This expert's or this sender's ideal action is this point over here. Now, these equilibrium strategies are such that by changing his own message, this expert will be able to alter or vary the action chosen by the receiver along some line, and that is this blue line which I have drawn. Okay, so this is the true state of the world. The action choice of the receiver will depend on what this expert says, and provided the other expert is following his equilibrium strategy, this expert will be able to change the action along this blue line. Right. Now, we have chosen the equilibrium strategies in a way that the following property holds. This blue line is at 90 degrees to the direction of his bias. Yes, and this you can check. You can derive the equation of this blue line from those strategies, and you will find that it is at 90 degrees. It is orthogonal to his direction of bias. And so, if the expert's ideal choice is this point, and he can only influence the action along this blue line, he will want to choose the point on the blue line which is closest to his bliss point. And since these are at 90 degrees, since this line is perpendicular to the blue line, that means that the true value of the state of the world is what he likes best on this blue line, right? He cannot make the action choice get any closer to his bliss point, right? This is the closest. And so therefore, he has an incentive to follow his equilibrium strategy, because if he follows his equilibrium strategy, he will end up selecting this point. And if he deviates from his equilibrium strategy, he'll go further away along this blue line to some other point, and that will be further from his bliss point. Yes, and this is true of both the experts. And so combining these two, each expert in this equilibrium, the first expert can change the action along the blue line, the second expert can change it along the pink line. None of them want to move away from this point. Okay, so both of them will send messages in a way that the true value of the state of the world is being selected. Another way to depict it is in this picture, in the earlier pictures. So these are the message strategies, right? So the first expert is basically reporting a number which is essentially selecting a line from a family of straight lines. So all of these straight lines have the slope minus b1 prime divided by b2 prime. Okay, those are the slopes of the first of these equations. So the first expert essentially, from this family of straight lines, points to one of them and says the true value of theta lies on this line. And the second expert, from a different family of straight lines, points to one of them and says that the true state of the world lies on this line. And when the receiver learns of this bold blue line and this bold pink line, he essentially combines them, looks at their intersection, and that tells him what the state of the world is. Yes, and we saw that both of them have an incentive to point at the correct line on which the state of the world truly lies. So the overall message of this analysis is what is it saying? To sum it up, it's pointing to the importance of diversity of opinion organizations and institutions. Yes, if people don't have identical preferences, there's an incentive for them to lie or distort or exaggerate. But as long as they're pulling in different directions, as long as their biases are different from each other, these different biases can be made to play off against each other. And from that, a lot of information can be extracted. So the lesson is that, echo chambers are bad. If these two experts had biases in exactly the identical direction, then we are basically back to a single expert case. And as we saw it with single experts, a lot of information gets jammed, a lot of information gets lost, right? And the contrast here couldn't be more dramatic or sharper, that when they have different biases, the interaction of their diverse ways of distorting the message or lying in different ways kind of cancel each other out. Somehow they neutralize each other, their different biases and their incentives to distort the message, so that the truth actually shines through that. So decision makers like CEOs or prime ministers or presidents, things are not lost, things are not bad if they can't find advisors who share their preferences exactly. But as long as they can create diversity in their cabinet, in their advisory bodies, that holds a lot of promise and can lead to very informed, very efficient